Hey AP, this video is on electrons and photoelectron spectroscopy, or PES. So yesterday we talked about mass spectroscopy, where we looked at the different masses of elements or compounds, and we sorted them based on how heavy their nucleus were. And this time we're going to look at where the electrons are, and we're going to get different readouts. It's going to help us determine what element we have based on where its electrons are located. So as we move forward in just about everything we talk about in chemistry, we're going to resort back to Coulomb's law. And Coulomb's law talks about the force between two charged particles, and that force is inversely proportional to the square of the distance between them. That's a lot of jargon just for us to say that when things are closer together, they're going to have a stronger force than when they're further away. So if I have two particles, and we call them Q1 and Q2, if they have the same sign, we know that they're going to repel. And if they have opposite signs, we know that they're going to attract. And this makes sense that our force is stronger when they're closer, right? Two of the same charged particles get close together. They're going to repel. We're going to feel that repulsion. And then two particles that are opposite in sign, when they get closer, they're going to attract. And as they're further away, they have less attraction between their elements. So this is the formula for that. We won't do any calculations with it, but it's just good to know where that came from. Now, this starts to really play into effect when we talk about Bohr's model. And we know that Bohr came out and said that electrons travel in fixed orbits or shells around the nucleus. And if we heat those elements, we can start to see electrons change in energy levels. So for example, if a gas is heated, and I have an electron here on my second energy level, when it's heated, my electron will absorb energy and move to a higher energy level, into a higher shell. Then, as my electron relaxes back down, because it's not going to stay there once the energy coming in stops, it's going to relax back down. When it relaxes back down, it emits a photon of light. And this little squiggle is how we show photons of light. Now, depending upon where this transition takes place, and depending how big that transition is, we're going to give off different colors of light, and we are going to see different lines in a light spectrum. And we can quantify, and people have quantified, where those changes are in energy levels, and we get different series of light. So we can see that here we have the Lyman series, and in the Lyman series, we are going down to energy level 1 for all of these, so to 2 to 1, 3 to 1, 4 to 1, and 5. We can see that with energy here, it takes more energy to go from the first to the fifth energy level. It's a much bigger jump in energy levels or shells than it is to go from 1 to 2. Same thing here, going from 2 to 3 is much smaller than 2 to 5. 3 to 4 is smaller than 3 to 5 here. So these are different series that we can use to analyze to see where our electrons changed. Now, electrons have wave-particle duality is what it's called, and that is where we can say that electrons behave like a particle, right? So I can say this dot moves here and down, but I can also say that an electron is light waves, okay? So it has both things. So here I have my wave, right? And we've seen a wave before, and different parts about a wave we can measure. We can measure the wavelength from crest to crest, and that we show as an upside down y, which is a lambda. And remember, we measure wavelength in nanometers. Then we also have our frequency, or the number of waves per unit of time. So we have this number per second, or hertz is another thing we could use. Also note that you can measure wavelength from crest to crest, or this middle part here as well. And this skips because this is half a wave and this is the other half of the wave, right? We need the top and the bottom. And then remember, c is the speed of light. It's a constant, 3 times 10 to the 8th meters per second. And I know I said yesterday that Avogadro's number isn't in here, but it is. I just missed it. It's up here, 6.022 times 10 to the 23rd. The speed of light is also in here. So if you want to use this to more digits, 2.998 times 10 to the 8th. 3.0 times 10 to the 8th is basically the same thing. So either way. And then we can do calculations about wavelength and frequency using our speed of light equation. And this is something that we have done previously in chemistry. Furthermore, we can look at different wavelengths and frequencies. That's what comes up next. So then we have our high frequency, things like cosmic rays. And as we get lower in frequency, we then have radio waves. Remember, high frequency is things that are really, really close together. And then long wavelength, low frequency, these are things that really start to mellow out in terms of waves. You won't have to memorize this, but you should know things like your visible is here. Ultraviolet is on the violet side of visible. Infrared is on the red side of visible. So in this case, our Roy G. Biv is backwards, right? From red to violet. If we can remember that infrared is longer waves than ultraviolet, right? Ultraviolet X-rays get smaller. That helps us remember our reds versus violets in terms of wavelength and frequency. So you want to have an idea about where these are, but most of the time you're just going to be doing calculations with them. So continuing on with our pursuit of studying electrons, many different people have come about and studied where electrons are. So they're continually trying to improve upon Bohr's model that said electrons go in rings. And then Schrödinger came around and said, well, I don't think they actually are in rings. I think we can actually use math to figure out probable locations about where they are. So he used math, specifically calculus, to figure out where the electron is found. And we call this the quantum mechanical model. And you can take an entire course on the quantum mechanical model in college. It's kind of fascinating. He also worked with Heisenberg, and Heisenberg made his uncertainty principle. And he said, well, we might be able to know where it is, but I can know position, but I can't know momentum. So I can't know both momentum and position at the same time. I can only know one. And that's because if I look at my electron and I see like where it is, that's a pinpoint in time. Boom, it's there, but I don't know how fast it's going. Or I can measure how fast it's going, but I don't know where it is exactly in that time. So we can only know one or the other. Okay. Then thinking about where electrons are found, they're found in varying smaller locations. So we have the shell, which is the energy level or the location where the electron is found. We can have the first shell, the second shell, the third, and the fourth. That shell is divided into subshells, which is where we get our S, P, D, and F subshells. So we have things like 1s or 3p. Right? We've seen that before. 3 being our shell or energy level, P being our subshell. Then furthermore, we can get into orbitals, which are parts of our subshell. So remember in our S subshell, we can have 1 orbital. In our P subshell, we can have 3 because we had 3 lines to put electrons. Each one of those orbitals holding 2 electrons. D's can hold 10 and F's can hold 14. And then we can also look at their spin. And because of the Pauli exclusion principle, we say that 2 electrons in the same orbital have opposite spins. And that's so because otherwise it would spin out of control. So one spins one way, the other one spins the other way, and that keeps them balanced. Okay. This is then a chart of how that breaks down. So I have my shell numbers, the number of subshells I can have, which correlates to the shell number. Their subshells, my 1s, 2s, 2p, 3s, 3p, 3d, 4s, and so on. Number of orbitals, max electrons, whole electrons. And this is just a summary of how we figured out electron configurations and orbital notations last year. And we'll go over that in a second here at the bottom. Remember that to fill an orbital, we follow Aufbau's principle. And he said that we fill the smallest energy level first, and then we use Hund's rule, where we put 1 electron in each orbital before we start pairing them up with opposite spin. So let's quickly do a crash course of electron configuration, noble gas notation, and orbital notation. So looking at copper, on the periodic table, copper is here. Now remember, we can break our periodic table into sections by moving helium over here, pretending it's there. This section is my S block. Here is my P block. In the middle is my D block. And then this is my F block. Remember that electrons or energy levels going out for S is 1, 2, 3, 4, 5, 6, 7. P is the next energy level, and we can see that here, right? My P starts at 2. So I have 2, 3, 4, 5, 6. My next orbital in energy level is D, so it starts with a 3, 4, 5, 6, and then F will start with 4, and then 5. Okay. Now I read left to right, and I continue just going across. So if I want copper, I start at the top. I have 1s, 2 across, so 1s2. Moving down, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Noble gas notation is our shortcut, is where we go up and over to our previous noble gas. So copper up and over is argon. So argon goes in brackets. And then everything that comes after argon we report. So after argon comes potassium. So that's 4s2, 3d9. So argon, 4s2, 3d9. And then finally, we have our orbital notation, which is just where we show all of our orbitals and where our electrons are based off of our electron configuration. So S has 1. So I've got 1s, 2s. P has 3. Again, S has 1. P has 3. S has 1. And then D has 5. See, 3D, 5. 1, 2, 3, 4, 5. So I fill starting at the lowest energy level first. 1 up, 1 down. 1 up, 1 down. Up, up, up. Down, down, down. Up, down, up, up, up. And then at my end, I have 3D9. So they're going to fill 1 up in every spot first. Then I'm going to come back and start pairing up. So that's 5, 6, 7, 8, and 9. So that's my orbital notation. All right. Moving on to thinking about how does this change if I have an ion. Okay, so how would my electron configurations change if I had copper plus 2? Well, plus 2 means that I lost 2 electrons, and they're going to be lost from the highest energy level. Or another name for your energy level is your highest shell. So those are our numbers, 1, 2, 3, 4. And I have energy level 4. So in this case, I'm going to lose my 2 electrons from the 4s. And 4s, S is a subshell. So the 4s subshell. So for example, my electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. These I lost, but I still have to say that it's empty. So 4s0, 3d9. Okay. If this had plus 3, they would come out of my 4s, and I'd still have to lose one more, and my next highest energy level is 3, and of those, my highest subshell is the D, so this would come out as well. So 1 would be lost from there. Okay. All right, so most of that was review. Ions are probably a little bit new, but they should make sense based off of what we know about ions. If they're positive, we lost electrons. If they're negatives, we gain electrons, and we can gain them to the highest energy levels as well. But now let's get into something brand new, photoelectron spectroscopy. Photoelectron spectroscopy we refer to as PES, and this is based off of the photoelectric effect, which means that electrons in an atom absorb enough energy to overcome their attraction to the nucleus, and then we can eject them from the atom. So this plays into part the amount of energy required to remove electrons from our elements. So how we ionize them similarly too. So we have our formula for energy. Energy is always in the form of photons in terms of electrons and light. And we have energy is equal to Planck's constant times frequency. Planck's constant, also a number given to you on your sheet, which is here, H. Also, your formulas for atomic structure, energy, and light are here. So you don't have to memorize them, you just have to be able to use them. Then I've got frequency, again, 1 over S, and then energy is in joules. So this energy that we put in must exceed the ionization energy and overcome the attraction to the nucleus. Again, Coulomb's law. My electrons are negatively charged. They are going to be attracted to my protons in my nucleus. The closer they are, the more tightly they are attracted, or the stronger they're attracted, therefore the more energy is required to remove them. Okay, and we're going to see that in our printout here below. When we're reading a PES spectra, okay, that's plural for a spectrum, we are going to notice that we have large peaks, and we can see that here. These are each peaks, okay? This is energy along the bottom, and notice that it's backwards, okay? My smallest numbers on the right, my biggest numbers on the left. And then my y-axis is the relative number of electrons. Notice that it's relative. So that means that they are proportional to each other. Okay. So the taller my peak is, the more electrons I have present. Now, the reason that we put it this way is that way it matches up with our electron configurations. We just said that electrons closer to the nucleus are more attracted to the nucleus and are going to require more energy to remove. So that means that I'm going to need to use more energy to to remove my innermost electrons or my core electrons. So that's why this peak is at a higher energy. This first peak for every spectra is going to be 1s2. Okay? And that means that this is worth 2 electrons, the height. So this is 1 electron, 2 electrons. So it's worth 2 electrons. This next peak is the same height. So this is also 2 electrons. And we know that the next group of electrons in our electron configuration is 2s2. Notice that this peak is 3 times as big as this one. So each one of these is 2 electrons. So 2, 2, 2. That makes 6 electrons represented by this peak, which makes sense because the next one in our electron configuration is 2p6, those 6 electrons. Then after that, this one is also looks to be the same height as this one, as 2. And we know that next is 3s2. So again, left to right, this requires the most energy to remove because it's a core electron. It has really, really, really strong attraction to the nucleus because of Coulomb's law. Okay, Coulomb's law is going to be the answer to many of your questions tomorrow. Whereas if we go farther away, these electrons, so much further away from the nucleus, they're hardly felt, they hardly feel the nucleus. There's less attraction, so it's way easier to pull one of those off than is to pull off a core electron. All right, neon has an electronic configuration, 1s2, 2s2, 2p6. Pretend these are superscripts. How many unique peaks are expected in neon's PES spectrum? Well, we know that there's 1 peak for each shell that we see, and more specifically for each subshell that we see. So each one of these would be a peak. 1s2 would be a peak, 2s2 would be a peak, and 2p6 would be a peak. So there would be 3 peaks. Your 1s2, your 2s2, and your 2p6 would all be peaks. Of those, which electrons correspond to the largest energies? Well, those will be your core electrons. And in this case, your core electrons are going to be your 1s2 electrons. Okay. Which of the peaks are going to have the greatest intensity? Intensity being the largest. Well, we know that the greatest intensity has to do with the number of electrons in the subshell. So my subshell with the highest number of electrons is my 2p6 because I have 6 electrons. Okay. So again, photoelectron spectroscopy, electron is just our electron configurations and the energy required to remove those electrons. What would it take to remove it? Which then gets us into ionization energy. And ionization energy, which we've talked about before last year in chem, is the energy required to remove an electron in kilojoules per mole. And we're going to see that there's a large jump in ionization energy from the second to third electron because you're moving to more core electrons that are closer to the nucleus and have more attraction to the protons in the nucleus. And we can see that here, right, from our outermost electrons here compared to our next one. This is a big jump. It's almost a 10-fold jump from here to here. Then again, we go from our 2 energy level to our 1 energy level, again, coming out another shell in. That means here again, we go up another 10-fold jump to the 100s. So almost every shell, it seems like we're changing a 10-fold difference of increasing in energy level. Energy required to remove those electrons. And we'll study this more in our next set of video notes where we analyze what does this pattern look like. Some other terms to know, paramagnetism is a term that talks about if it's attracted by a magnet, which means there's unpaired electrons, so they're able to attract. Whereas diamagnetism is where things are repelled by a magnet because all of their electrons are paired. And then finally, we have something called an isoelectric species. And these are 2 species with the same electron configurations, but different numbers of protons. So if I looked at the electron configuration of something like neon, so neon has an electron configuration, 1s2, 2s2, 2p6, okay? Sodium continues on to be 3s1. However, for sodium to be an ion, Na+1, it loses its electron in its highest energy level and orbital, which is its 3s electron. And so really, that's gone, so it has the same number of electrons as neon. Similarly, if I had fluoride ion is F-1. Typically, it would have ended here. However, by adding in that 1 extra electron, that gives it 1 more electron than normal to give you the same number of electrons as neon. And we can write those out. So if I have neon is 1s2, 2s2, 2p6, sodium +1, 1s2, 2s2, 2p6, 3s0 because it loses that last electron. And then fluoride, 1s2, 2s2, it would typically be 2p5, but I've added in 1 more electron to make it an ion, so it's 2p6. As always, if you have questions, make note in your notes. Circle things, highlight things, make a note of it, and then we'll touch base on those when we get to class tomorrow. Good job.